All right. So today we are going to make our second step in studying control theory. Last lecture, we focused almost entirely on the models. The question was, how do we model a specific system which we would like to work with, right? How do we model that system? And the answer that we gave, good enough for now, was we model it with ODEs and state space models. So we proposed those two ways to do it. Specifically, we talked about linear ODEs, and state space models by the nature are linear models. All right, so that was the answer to the question, how do we discuss the objects that we want to control? For now, we proposed those two models. Now we can make a next inquiry, and that is, what do we specifically care about when we work with those models? What do we specifically care about? And there is a good answer to this question. Sometimes it is difficult to answer questions like this. What do we care about? Sometimes there are great many things. We want this, right? With control theory, we have a specific answer. There is one thing that we care about a whole lot, and this property is extremely important. This is a property of stability. Stability. All right, let us go right into it. So before we discuss stability, we need one concept, and that is the concept of a critical point, or what we call a node. Right. So let us consider ODE. X dot equals f of x t. Okay, so x dot equals f of x t. Then let us find such x0 that f of x0 t is equal to 0. Right. Such state x0 is called a node or critical point. So what does it mean in plain language? It means that at the point x0, derivative of the system is equal to 0. Okay? So at the point x0, derivative of the system x dot is equal to 0. Or the same in different words. What if we are already at x0, we're not going to leave x0 because dx dt is equal to 0 at this point. So we are always going to stay at x0 once we are already there. This means that x0 is not only a critical point, but also a solution to this equation. Since x equals to x0 satisfies this equation. Okay. At least forward in time. Right? Forward in time, it satisfies this equation. Okay. Sounds quite interesting. You know, is possible to imagine such solutions? All right. All right. Well, if you want a physical example, you can think about it this way. Imagine you have a pendulum. Here's my drawing of a pendulum. And it is described by some dynamical equation x dot equals to f of x. Well, very specifically, this there is one position where the pendulum is vertically down, right? And not only it is vertically down, but its angular velocity and linear velocity is equal to 0, right? That is a position which is a node. Once we are in this position, the kinetic energy is 0. Mechanical energy is the lowest it can be. the potential energy is lowest that can be. So the total energy is at its lowest state. That means it's not going to move anywhere, right? Unless external force acts on it. But if there is no external force, then it always is going to stay there. That is a node. That is a node, right? There is another equilibrium, upper equilibrium, where the total energy, potential energy is maximum, and the kinetic energy is again 0. That is also a node. Upper equilibrium is also a node. But you can see that those two nodes are slightly different, whereas the lowest equilibrium is somehow feels natural. The upper equilibrium somehow feels a little bit questionable. We will understand those feelings in just a second. But yeah, this is an example of a node that's low equilibrium position. Do we have questions about this point? Okay. Now stability. The node x naught, x0 is called stable if and only if for any constant delta there exists another constant epsilon such that x of 0 minus x naught is the difference between x of 0 and x naught being less than delta implies that the difference between x of t minus x naught will be less than epsilon. Let me say the same thing, but in more human terms. If initial condition is delta away from x naught, from the node, then any x in the remaining solution, like in the solution going forward in time, will be less than epsilon. Okay. So if the initial condition is inside what we call delta ball, right? So it's a delta away from the node, then the rest of all the solution going forward will be at most epsilon away from the initial condition. Does it make sense?
What are the values of delta and epsilon?
What are the values?
Yes.
What we are saying is that for any constant delta that you can choose, so you choose what delta is, there should exist some constant epsilon. So epsilon is not specified. So delta you choose, epsilon should exist, it's just not specified. Okay. That might be maybe better illustrated in a drawing. Drawings are a little bit hard. Like, you know, how to draw something convincing. But let me try. Let's say your node is, I'll draw it in red, is something like this. Okay. The horizontal line is time here. Red is, I don't know, do you see red? Let me make it bolder. Okay. This is a node. So as long as your solution stays on red, it's not going to leave it. Okay. Now, let's say you have a solution which starts, I'll draw it in different color, say blue. That starts somewhere here. Okay. Your solution goes something like this, let's say, then maybe like this. Then what is the delta and what is epsilon? Like in this case, you can say, okay, let the delta be this distance, for example. Not exactly to the solution, slightly bigger than the initial condition. If you can prove that for such a delta, you would have all solutions within, let's say, epsilon distance, which I show in maroon now, from the node, then you proved stability, right? If I wanted to be as tight as possible, like I wanted to be more attuned to the solution, I would have said, okay, this is a delta, right? I could have said, okay, this is the epsilon, right? This is the biggest distance we saw on this particular solution, right? And that was the distance from the origin of the solution. But all of this is nice and good, except we don't know if the solution that is closer to origin won't have a bigger spike. You know, it could. So it is not a game of finding how far one specific solution is from the origin and how far it deviates from the origin or from the x node somewhere in its duration. The game is to prove that within some ball of size delta, all the solutions that start from there would not deviate more than epsilon away from the x node solution. Okay, that is the game. Okay. All right. So equivalently, we could say it even simpler. We could say the solutions starting from delta size ball do not diverge. Right? Solutions starting from delta size ball do not diverge. That is another way to say the same thing. Okay. All right. Good. Now, related concept, but very important. Let us let X have like a node x0. So this node will be called asymptotically stable. Asymptotically stable. If for any constant delta, it is true that if there exists such constant delta, it is true that the initial condition being delta away from x node implies that the limit of x of t approaches x node. So let me put it now in normal language. If we are only delta away from our x node solution, it means that we will converge to x node as time goes to infinity. So our solution, our graph would be, I will draw it here. If we have our x node, I'll draw it now in brown here. If that's our x node, what we would expect is that any solution from the region delta, so delta away from the x node, would eventually converge to x node. Okay. So it would slowly but surely converge to x node. So as time goes to infinity, they will get closer and closer and closer to x node. Right? And that should be true for some kind of region delta. Right? It doesn't have to be true for Mikhail. 1 second, I will answer your question. So it doesn't have to be true for all space. It has to be true just for some region delta. Yes, Mikhail.
Can you provide us some counterexample for stable, but not asymptotically.
Mhm. Okay, good question. Good question.
Am I correct that it's like no damping oscillation?
Yes, exactly.
Yeah.
That is not oscillation without damping is a good example. Yes.
Thanks.
No, thank you for the question. Let me reiterate what we just said. So let's consider a oscillation of a pendulum. Okay. Oscillation of a pendulum. This oscillation, if it is has a damping, so some friction force, it's going to decrease in magnitude, and eventually it is going to approach the lower equilibrium. Okay. If there is no damping, it's not going to decrease in magnitude. It's going to continue oscillate like before to infinity. So if there is damping, it approaches this lower equilibrium solution, which is a node. All right. That will be a asymptotically stable solution. If there is no damping, it oscillates infinitely. It means it doesn't approach anything, so it's not asymptotically stable, but it is still stable. Why is it still stable? Well, because it does not diverge. So it stays epsilon away from the solution. In fact, you could say compute what epsilon is for a pendulum. Let's say if the initial angle is, let's say, pi over 3, right? And there is no external, and the initial velocity is 0, and there is no external force, then it's going to stay at most pi over 3 in terms of position from the initial conditions. What is velocity? Well, you can compute the velocity as it passes through position pi equal to phi equal to 0, right? So for a pendulum, you can easily find the maximum velocity it's going to have, the maximum angle it's going to have during the oscillations. And those constitute your epsilon pole, right? And yeah, so that's how you estimate epsilon for the previous example, right? But if it has friction, instead of talking about epsilon, notice this definition does not have epsilon, right? This definition does not require any epsilon. It only requires convergence to the node. So if you have friction, all you need to show is that it eventually will converge to x equals to 0, right? Phi equals to 0. So that is a classic two examples of asymptotic stability and stability. Okay. So the simplest way to say it is solutions starting from a delta-sized ball converge to the node. That is asymptotic stability. Any questions about it? Okay, no questions, I think. So let's go on. Let us go on. Okay. So here are just very simple examples. So let us walk through them. Consider a system x dot equals to 0. If it has a solution x equal to 7. Is a solution? Yes, we can substitute it there. X dot is equal to 0 indeed for the solution. And the solution is stable. Like it doesn't diverge. It doesn't do anything, just constant. But it's not asymptotically stable. Why do I say that this is not asymptotically stable? Well, we can consider a different solution in the delta ball around this one. So for example, here's a solution that at the point x of 0 is equal to 7 plus delta. Okay. It does not diverge from x equal to 7, but does not converge to it, right? It will be just staying equal to 7 plus delta. So is also a solution. It is stable, just not asymptotically stable. Now, before we go on, let me introduce a piece of terminology. When a system is stable, but not asymptotically stable, we call it marginally stable. Marginally stable. Okay, marginally stable. Sometimes we can call it stable in the sense of Lyapunov. Technically, asymptotic stability also implies stability in the sense of Lyapunov. So saying stable or stable in the sense of Lyapunov is the same thing. But in kind of like informal speech, what we usually do is we say the system is stable. How is it stable? It is asymptotically stable. Or system is stable. How is it stable? It is marginally stable, or stable in the sense of Lyapunov. So often we say stable in the sense of Lyapunov or marginally stable to indicate that it does not converge. So it's not asymptotic, but it is still stable. Okay, that is a typical usage. So this would be a marginally stable system, or example of a system stable in the sense of Lyapunov. Notice also that to be concrete, I cannot say that the system is marginally stable. I should probably say that the solution x equal to 7 is marginally stable, because the stability somehow talks about specific solution, not about the whole system. Right? That is a detail we need to keep in mind for about a couple slides. So let's do it. Okay, let's consider another example. X dot is equal to minus x. It has a solution x equal to 0. So this solution is stable and also asymptotically stable, because all solutions will converge to x equal to 0. Why is it so? Can someone tell me what the solution to this equation is? And someone tell me. Like x of t, what is it equal to?
It's e to the power of minus t
To the power of what?
minus t.
Minus t. Okay.
Yeah.
Yeah. Mhm.
And constant.
Constant, is it multiplied or added?
Multiplied.
Multiplied, okay. Correct. So the solution is constant, which is initial condition in this case, times e to the power minus t. As you can see, e to the power minus t will tend to 0 as t goes to infinity. So no matter what constant we choose, we will always tend towards 0. So every solution will approach x equals 0, right? C depends on the initial condition. C is essentially is initial condition. Like C is x of 0. So, but no matter what x of 0 we take, any delta size we take, will still approach x equal to 0. So not only it is asymptotically stable, there's also globally asymptotically stable, meaning that we don't need to talk about specific delta size. Any delta will suffice, no matter how large. That is called global asymptotic stability. Okay. Now, one more example. So consider dynamical system x dot equals to x and solution x equal to 0. So this system is unstable. Why? Someone please tell me what is the solution to the system.
Constant terms, e to the power
e to the power t, right? E to the power t. Thank you. So it's the same, just t without minus. As time goes to infinity, e to the power t goes to infinity as well. Right? Plus infinity to be precise. Right? So what we have is no matter which initial condition we take, as long as it is not equal to 0, we're going to diverge. If c is bigger than 0, it's going to diverge towards plus infinity. If c is less than 0, it's going to diverge to minus infinity. No matter how small delta is, any initial condition which is not exactly equal to 0 will lead to solution diverging. So that means there is no stability, no delta that would give us stability, right? And we cannot find such epsilon that would contain the entire solution. Such we sometimes call it epsilon tube. Like initial disk of delta produces kind of like a tube of epsilon, right? We cannot say that there exists such a disk of deltas for which we can find any tube of epsilon which would contain entire solutions. They always kind of go in all directions. So this system is unstable. Okay, this system is unstable. Good. Good. Any questions about it? By the way, today we'll maybe try a small experiment. We'll have after like in a few slides, we'll discuss one more, a little bit more mathematics. Then I'll give us like a 7-minute break, and then we continue. We'll just see if a break in the middle of like mathematically heavy lecture helps. Okay, and it doesn't always help. Like I know that often enough students tell me break doesn't help, especially because it is online lecture, etc. You're already relaxed. But let us just see if it helps when the lecture is heavy on mathematics. Okay, you can later tell me in the chat how you feel about it. We just try it once. If you don't like it, we don't have to do it. Okay, let's go on. Now, what we have is now like our specific familiar state space systems. Right? Let's think about stability when applied to those. Okay. Let us consider this linear ODE. This is linear time invariant system, LTI. The reason we call it linear time invariant is because first is linear with respect to decision variables, is linear with respect to state and with respect to control. Why do we call it time invariant? Time invariant. Well, because A and B do not depend on time. There are time invariant systems where A and B matrices depend on time. Okay, so those two different classes of systems. Now, if we remove the input, so we get rid of this part, BU, we get even simpler system, x dot equals to AX. On top of still being LTI, so linear time invariant, it is also autonomous. It's also autonomous. Autonomous means it does not depend on anything except the state. So previously, you could say that here there is BU, and U somehow depends on time, maybe. Maybe U depends on time. So you couldn't claim that it depends, like what it depends on, right? You cannot say, oh, the system depends entirely on its state. Like we don't know what U is, right? So we cannot make claims. But here we can make claims. This equation does not depend on time. There is no explicit time anywhere. Of course, X as a solution would be a function of time, but time itself is not a part of its ODE, right? Does not figure in the ODE as an independent variable, as a variable out separate from the state. Okay, So we call it autonomous. We call it autonomous. Autonomous essentially in the literature is used, this word is used to imply that as long as you know X, you know everything about the future behavior of the system, right? With this system, you cannot know all the future behavior without knowing also U. But here, just knowing X is sufficient because you can solve it forward. It is a Cauchy problem, essentially. If you know X, you can solve it forward, and there will be no trouble. Okay. So that is what it means to be autonomous system. All right. Now, let us consider stability of linear time invariant autonomous systems. That sounds oddly specific, but you will soon realize next lecture, I think, why it is completely general and makes perfect sense. But yeah, stability of autonomous LTI. Autonomous LTI. Let us consider first a very simple case. We consider this autonomous LTI, x dot equals to dx, where D is a diagonal matrix. So not any matrix, diagonal matrix. It's really good. Okay. If we multiply x by a diagonal matrix like this, what we get is the x1 will be multiplied by the first diagonal element, d1. Then x2 will be multiplied by a second diagonal element, d2. And the result would look like this. It essentially will be a system of equations where x1 dot is equal to d1 x1, x2 dot equals to d2 x2, and xn dot equals to dn xn. That's what we're going to get. This is clear that this would have this form. So what is interesting about this equation is that it is a system of equations which are independent of each other. So we don't have to solve them simultaneously, we can solve them individually. And each of those equations have an exact solution. So the exact solution here is x sub I equals to c sub I times e to the power d sub I t. Basically, it says any x is equal to initial condition for this x plus exponent to the power d sub I times t. So there is a d corresponding to this x. It would be in the power of e. It will be exponentiated. Okay. Now we remember we already saw it once. This exponent. What we remember is that it diverges from 0 if d is positive, but it does not diverge if d is not positive, right? As long as d is not positive, it is not going to diverge. For example, if d is equal to 0, then solutions would be x equal to initial condition, right? And here it would be x1, for example, equal to 0. Where you saw it, it doesn't. That was the first example, right? And even more specifically, if d is less than 0, it converges. So we can clearly make a statement. Let me see if I have a separate slide. No, we can make a statement. If d is strictly negative, all those solutions will converge to 0. If d is at least somewhere equals to 0, but the rest, like if d is negative or 0, and at least some of those d's are equal to 0, we're not going to converge to 0. Some of the solutions will just not diverge. So the first case where all D's are negative is clearly asymptotically stable. The solution x equal to 0 is asymptotically stable. Whereas the case where at least some of the D's are equal to 0, that is marginally stable. Now, if at least one D is bigger than 0, then the system diverges. So it is unstable. Now is as good time as any to make one observation. In the original definition, we were talking about stability as a property of a solution. X equals to x naught. X equals to x naught. Let's go one slide back and consider what kind of a solution can this system have. What kind of solution do you think this system can have? Sorry, what kind of a node the system can have? A node or a critical point, if you want. So remember, critical point is such a solution where x dot is equal to 0. So what kind of critical point can the system have? Someone tell me. Mohammed Rizzo, I think I couldn't hear you. You were trying to speak, but I think I think maybe your microphones.
I wanted to say that when x is some constant, we have
If x is simply constant, like hash, x cannot be. You cannot say x is a constant because we're talking about a solution to differential equation. So you can tell me what x should be in at the initial point of time, right? And then if this x produces x dot equal to 0, it will be constant. But you know, you can't start with saying, oh, x is constant, because then you have I will have to ask you, what is x then?
okay, thanks.
No. But both ways we can approach the answer. This system 6, would have a natural solution, which is x equal to 0. If you put x equal to 0 into here, right? You put here 0. What we would have is a times 0 is 0. Right? So x dot would also be equal to 0. So that is a critical point or a node. Okay. But also any solution in the null space of matrix A would also produce 0. So we have family of solutions, x equal to 0 plus the whole null space of matrix A. If you don't remember what null space is, or you feel like, oh, suddenly we have algebra attack here, just ignore it. Concentrate on x equal to 0. Yeah, but there's nothing too difficult about null spaces of matrices, so you can refresh after the lecture if you want. If you want suggestions of what to read on those, I can give you. Okay. Now, x equal to 0 is a natural solution to the system, and for any system of this type, I didn't specify what A is. For any system, x equal to 0 would be a natural solution. Now, let's say there is such x. Okay, so let's just consider x equal to 0 for now. Okay, let's consider just x equal to 0 for now. We will soon find out that all of those discussions will work for any solutions. So we wouldn't have to discuss them, right? But for now, let's just keep in mind the solution x equal to 0. Okay, x equal to 0. I guess we can make one more convenient observation here while we work with such a simple system with a diagonal matrix D. If D has elements which are not zero, like all elements D are not zero, the only x that can make x dot equal to 0 is 0, right? There is no other x that can possibly deliver us to a critical point, only x equal to 0. But if at least one of the d's is equal to 0, so let's say d1 is equal to 0, then any vector of the form, so again, let me remind you what I mean, what I'm talking about. If d1 is equal to 0, let's say, then any x of the form, I don't know, let's say q 0, 0, 0, 0, 0, would be a solution, would be a critical point. So it doesn't matter what the first element is, because when you multiply it by this D matrix with 0 in the first diagonal, it's going to be x dot is still going to be equal to exactly 0, right? So for a system where some element on the diagonal is 0, right? We have a whole family of nodes in critical points, right? So we have not one critical point, we have many. But we just said that such a system, if it has d equals one, at least one d is equal to 0, it's going to have a solution which is only marginally stable, not asymptotically stable. So somehow, like in this case, when we can discuss multiple possible solutions, we already know that for any of those solutions, the system is going to be only marginally stable. So we can pick one, but the system is going to be marginally stable. It's not going to be asymptotically stable. This property will be able to prove that it holds for any linear system. In fact, the general statement will be like this. For a linear system, it is either asymptotically stable for all solutions, or it is marginally stable for all solutions, or it is unstable for all solutions. We wouldn't be able to come up with a linear system which has one solution or critical point which is stable, and some other critical point which is unstable or marginally stable. Either all of them are stable or none of them are stable. Okay, this is just an easy illustration with a simple example. To prove the same for general matrices, we just need a little bit of linear algebra. Okay. Do you have questions about? Let's go on. Now, let us consider autonomous linear time invariant system discussed by this equation. Okay. Discussed by this equation, where A has a eigen decomposition, so a decomposition into eigenbases and eigenvalues of this form. So what is this eigen decomposition? D here is a matrix of eigenvalues, okay, diagonal matrix of eigenvalues, and V is a what we call eigenbases. It's basically a matrix of eigenvectors that are stacked next to each other. If you're not familiar with it, the way you produce this decomposition is you write a definition of what it means to be an eigenvector. It is AV equals to, let's say, dV, where D is an eigenvalue, V is eigenvector, A is your matrix, right? you write all of those equations for each eigenvalue. You have n equations, and you rewrite them in such a way that you stack them horizontally. So this would be like, let's say, the first equation. AV is a vector, right? It's the first column of the equation of the matrix equation. DV on the right is also a vector. Then you stack the next column to be then the next, and you would get an equation of the type AV equals to. Let me make sure I don't say anything stupid. I think, yeah, it's like this. It will look like this. Yeah. That's what you're going to have after you stack them together. And then you multiply both of them by V on the V inverse on the left, and you get eigendecomposition. Okay. So it's possible. It's possible to do it like this, and this is possible for any matrix where you have yeah. Okay, let me just go into of like too much algebra, but basically for systems with real eigenvalues, it is always going to be possible. It's always going to be possible for systems with real eigenvalues. Okay. If like real distinct eigenvalues, so okay. So we have this eigendecomposition. Now let us put it into this system instead of matrix A. So we have matrix A here. Instead of matrix A, we put this V times D times V pseudo inverse here. Now we can multiply both sides by V pseudo inverse. One second. So we multiply by V pseudo inverse here and here. What we have is V pseudo inverse here, V pseudo inverse here. Right? And what we notice is that we can cancel this part out. V inverse, sorry, not pseudo inverse, V inverse. And then we can make a substitution. We can make a substitution. Z equals to V inverse X. Okay, let's suggest we define a new variable, which is equal to V inverse times X. So the equation then becomes like, this is Z dot, this is Z. And the equation is basically Z dot equals to DZ. Okay, but this we already discussed previously. And we said that if elements of D are real, and we assume that it is a case of real eigenvalues. If the elements of D are strictly positive, if at least one of them is positive, system diverges. If all of them are strictly negative, system converges, so it is asymptotically stable. If at least one of them is zero, but they're all non-negative, then the system is marginally stable. Okay. So what I propose we'll do is I'll pause here. I'll pause on this slide so you think about it. And after we have a short break, like 5 minutes. Then we'll continue, but hopefully maybe with the questions here. Like this is like one of the maybe 2 remaining difficult ones, right? Okay, short break. So do you have any questions about this slide? Was it understandable? Mm-hmm. Please, someone will want to ask. Екатерина? Okay. So was it understandable what we have on the slide, like the way we moved on, like after looking at it a little bit more? I mean, we have a system for which we have this very specific decomposition, right? We rewrite it with this decomposition. Then we do two interesting steps. One, we multiply by V pseudo inverse on both sides, which allowed us to get rid of this V here, right? Then we make a substitution, which is V pseudo inverse X becomes Z, right? And this gave us the system that we previously studied on the slide before. And that allowed us to reason about how real eigenvalues of the system influence its stability. Okay, if there are no questions, let us move forward. We'll see like more complicated stuff. Okay. So we can have a specific type of matrix where eigenvalues are easy to find. Like here, I just said eigenvalues are real, they exist. Real, how do you remember, right? Real means like not complex, right? So complex is when you have imaginary numbers, right? Real is no imaginary component. Okay. So eigenvalues of a upper triangular matrices are elements on the diagonal. Okay, that is like one of those rare nice cases which we can use. So if we have upper triangular matrix, so matrices of this type, right? The eigenvalues, so why do we call them upper triangle? If you draw a triangle like this, it would contain all non-zero elements of those matrices. Right? Was a question in the chat? Okay, Ekaterina, I'll answer your question in just a second. Good question. I'll answer it in just a second. So upper triangular matrices, those where if I draw a triangle like this, it will contain all the elements, right? So all the elements are on the diagonal, non-zero elements, or above the diagonal. That's why we call them upper triangle. Okay. So eigenvalues of upper triangular matrices happen to be elements on the diagonal. So those are eigenvalues of upper triangular matrices. Okay. So if we go back to what we established in the previous slide, as long as we can have the same decomposition for this matrix, like this eigen decomposition into eigenbases and eigenvectors, eigenvalues, right? Then it would be exact same story, right? And the story would be that this matrix, like a linear system with this matrix, would be stable if all the eigenvalues are strictly negative. We're marginally stable if they are non-positive, some of them are zero, and it will be unstable if at least one of them is positive. Okay, it will be the same story as long as we can prove that there is a decomposition. In a second, I will, I will show you how we can prove this property without requiring this decomposition. Like the fact that eigenvalues on the diagonal influence the stability, we can prove it here without resorting to the proof on the previous slide. But let me first answer a question of Ekaterina. The question was, what was the purpose of the transformation from Z to X? I guess from X to Z, right? If the solution Z is stable, can we say that it is stable for X? Okay, that's a good question. Yeah, a good question. So the purpose of this transformation from X to Z is to get this simple system for which we already know the answers, right? We already know how to treat this system because we treated it on the previous slide. It is trivial. So that was the reason for substitution. Now, the better question is, that is the second part of the question that is interesting that I didn't address is, if Z is stable, can we say the same about X? That's a good question. That's a very good question. And indeed, it is possible. Why? Well, Z related to X through this equation. That means, we can write it here, that X is equal, if we multiply both sides by V on the right, X is equal to VZ, right? VZ. If Z converges to 0, okay, if Z converges to 0, X will also have to converge to 0, because 0 multiplied by any matrix, 0 vector multiplied by any matrix is a 0 vector. So it would converge. It doesn't have to converge as how should I put it? It doesn't have to be the same magnitude. It could be a very different magnitude. Usually it will be the same because since V is constructed of eigenvectors, we usually normalize them. So they're usually unit length. So V is also just happened to be a nice behaved matrix. It's not going to change size of X very much, right? Z and X would have roughly the same size. But even without this property, it doesn't matter. The convergence would still exist. And since it is a linear operator, we can even reason about like how the convergence would be, like the sequence of like values of Z would be very similar to the sequence of values of X in terms of the norms, etc. So it will be, you can think about it this way. Imagine you have the sequence of Z which converges to 0. Then you do linear deformation. It means, if you want to be very exact, it means rotation, stretching, and rotation. That is the linear transformation. What linear transformations do: rotation, stretching, and rotation. Right? Okay. It's still going to be, the sequence will be different looking, right? It can be rotated, can be stretched, but still going to be a convergent sequence, even if you kind of deform it. So yeah, convergence of Z implies convergence of X. And this comes from this relation because V is full rank. And V is full rank because we basically define matrix A such that it has a full rank eigenbasis. Okay. Okay. Hope I answered the question. Yeah. Thank you, Katerina. Now back to upper triangle matrices. For these matrices, we don't have to resort to this type of argument. We can do it simpler. Let me show. So consider LTI where we have x dot equals to mx, where M is upper triangle matrix with negative eigenvalues. So I just straight up tell you it's negative eigenvalues. So what we want to prove is that it is going to be asymptotically stable. So the last equation in this system is written as x sub n dot is equal to m sub n times xn. Okay. Because it is upper triangle, the last equation would be x multiplied by this only one element here, right? That's going to be equal to x or last x dot. So basically, the last equation looks the same as in the diagonal case, and for which we know how solution works. It's going to be e to the power m t, and we said that all of those eigenvalues are negative. Okay, so this is a negative number. That means that this solution converges to 0. So x n, as time goes to infinity, goes to 0. Okay, let's consider the equation above this one. Well, it is x dot n minus 1. And that is a sum of two numbers. Why? Well, let's look. Like the second to last equation would have two numbers, one here, so one diagonal number, and one off diagonal, right? Same as next one would have one diagonal, two off diagonals. Next, one diagonal, three off diagonals, right? Like in this case, it is one diagonal, one off diagonal. Makes sense. So this is the off diagonal number. Oh, no, sorry, is this diagonal number? So this is one of those eigenvalues. And this is one off diagonal number. Let us observe that this, I will show it in green. This is an eigenvalue. So this is a negative number. Okay. We don't know anything about x sub n minus 1. So this so far is a mystery. But we know everything we want to know about this guy. Sorry about it. About this guy. This guy approaches 0. So as time goes to infinity, this component will go to 0. And we are left again, one more time, with the equation exactly the same as in the diagonal case. X dot n sub n minus 1 equals to a negative value, negative number, times x n minus 1. So again, it is stable. It's going to, the solution is also going to approach 0 as time goes to infinity. And we can repeat it for all equations. All elements of the diagonal would always approach 0 because equations below them already proved that. And all we would have remaining is the element on the diagonal, which would, when we take exponent, would be negative because we, by definition here. And we would have a stable equation. All equations would converge to 0. So without any resort to those complicated like eigenbases, eigendecomposition, we can prove for upper triangular matrices that it's going to converge to 0 if all those elements are negative. It will be a little bit more challenging to prove, not like more challenging, but a slightly different process to prove, for example, that the system will diverge if one of them is positive, or the system will be marginally stable if one of them is 0 and the rest are negative. Right, but you can try to do it yourself. You can see the style of argument here. Okay. So this is just an example that you don't have to rely on eigendecomposition to prove those kind of properties. And more importantly, is just a reminder that for upper triangular matrices, independently we can say that there is this eigenvalue property. Okay. Now, before I move on, let me just say that in general, stability, yes, let me maybe skip, can I skip slide? No, I can't. Unfortunately, okay. Okay, spoiler for 2 slides ahead is stability in general depends on eigenvalues for any system, not only for upper triangular, not only for systems with the real eigenvalues, not only for diagonal systems. For all systems, it depends on eigenvalues. And now is important statement. I will repeat it later, but first time. System is stable asymptotically if all eigenvalues of the system have negative real parts. I'm not saying anything about complex component of eigenvalues. They can be complex, but I'm only talking about real parts. If they are negative, then system is stable, asymptotically stable. If they are negative or 0, at least one of them is, let's say, 0, we call it marginally stable. If real parts of eigenvalues, at least one of them, is positive, it is unstable. This is going to be true for all matrices. upper triangular, diagonal, with real complex eigenvalues, doesn't matter. Always going to be possible. Always going to be true. We will spend the rest of the lecture like discussing this point. We need to look at complex case, what happens. But this in general is the definition. Okay. Extremely important. We are going to have it on all exams and everything else. But also is extremely useful. Is one of those phenomenally useful ideas. Basically, what it means is, let us appreciate this fact right now. It means you don't have to solve equations. If you want to analyze how your solutions will behave, all you need to do is to find eigenvalues, which is done in most cases by something like eigen. Okay. Something like this. So just looking at eigenvalues, you can find if system is stable or not. It's quite impressive. It's quite impressive, and it is extremely useful. That's people use it all the time for all kinds of applications. So it is a very useful concept. Now, not only computationally it is very nice, but also how should I put it? Is a completely different quality of life. As you can imagine, you cannot check all the solutions from some kind of unit ball delta at infinitum, right? You cannot go on checking more and more and more solutions. It's pointless. It doesn't lead anywhere, right? Just checking any solution, looking if it stays inside some kind of tube or if it converges. You want to once and for all prove something about the system for all its solutions, for all initial conditions. Eigenanalysis, this is what I just showed you. That is what does it. You simply find eigenvalues. You don't have to solve system even once, and it's conclusive. Okay. So extremely important instrument here. Now, so far, we only proven this for 3 specific cases: diagonal matrices, matrices with real eigenvalues, and upper triangular matrices, which also happen to have real eigenvalues. Let's move on to complex eigenvalues. So let us consider. Do we have questions before I move on? I go fast. Do we have questions? Okay, I will move on, but interrupt me anytime or write in the chat. Okay, let us consider this system. This is a very specific system. We have alpha here, minus beta here, alpha here. Sounds interesting. This system happens to have 2 eigenvalues, which are alpha plus or minus I beta. Here we will denote x1, x2 as x. Okay. So is a 2-dimensional system. It has one pair of complex eigenvalues. Now we can make a very elaborate geometric argument here. Let me try to present it to you. I think it is convincing, but it is a little bit elaborate. So we start by making a claim that system will be stable only if dot product between x dot and x is negative. So that's a claim. I claim that dot product between this vector and this vector has to be negative. So they have to basically look at the opposite directions. Okay. How can we prove it? Well, x dot as a vector can be decomposed into 2 components. One component is x parallel, which is parallel to x dot parallel to x. And another one is x perpendicular, which is perpendicular to x. So let me draw it for you. So let's say this is x. I would write it like this, x. Okay. And let's say that in pink here is x dot. And this is dx dt. Now I can decompose this x dot into two components. One component is perpendicular to x. One component is parallel to x. And those two components, we will draw them in a different color again. Here's one component that is x parallel, x dot parallel. Here's another component that is x dot perpendicular. Okay. Okay. So far, so good. Like x dot is equal to sum of those two vectors. Next, by definition of what it means to be a dot product, this is equal to 0. So the multiplication of x with this vector, which is perpendicular to it, is equal to 0. I mean, dot product gives you 0 for perpendicular vectors. If you want to remember why, remember that one of the definitions of dot product is norm of the first vector times the norm of the second vector times the how do we call it, cosine of the angle between them. You remember, right? Cosine of the vector between them. So if the cosine is if the vector is 90 degrees, angle is 90 degrees, then cosine of 90 degrees is 0. So okay, this vector, remember, we're talking still about x dot. This vector here, what it does, it's going to rotate the vector x, right? It's going to rotate the vector x. Like instantaneously, it changes its orientation, right? It changes its orientation of the vector x. Okay. Now, this component, x parallel, so this component, it changes the x length, right? It increases or decreases x. We're talking here we're talking here about instantaneous effects, not about like long-term effects. Instantaneous. Instantaneously, one of them rotates x, another one increases its length. Now, if we know that this product is negative, it means that the length of x would actually shrink, because dot product, this would mean that this vector actually points in this direction, right? So the length of x will shrink. We don't know anything about this component. This component can be anything. Like this component can do anything it wants. It can rotate the vector x. We don't care. But this component will shrink it as long as this condition remains active. It means that x, as time goes on, will decrease in size until it approaches 0. Okay. So we don't care about how it changes directions, but we care about its size. And its size would have to shrink as long as this condition is enforced. Okay. So that is the geometric argument. I'm not sure if it is very convincing, but it's hard to come up with a even more convincing argument. So we'll have to make do with this one for now. Okay. So we've proven this statement. Now let me show you how from this follows stability criterion. Let us compute this thing. Well, this is equal to we can transpose it to have it x equal to x transpose x dot. This is x dot. This is x. And so this together is the same as this product. Now, when we multiply this by this, right? Then we multiply this again by this, we get a vector, right? Be alpha x1 minus beta x2, alpha beta x1 plus alpha x2, right? Then we multiply by this vector. Let me, I guess, write it out for you, just so it, I mean, maybe is a little bit more nice to see it, right? So we have alpha x1 minus beta x2. That is the first component. Second component is beta x1 plus alpha x2. And once we multiply it by this x1, x2, we have the brackets here. This will be times x1 plus, and here times x2. Okay, so this is what we will have when we open the brackets here. Then what we will find out is that this minus sign here, would allow us to cancel b, like this part, multiplied by x2 here. So it is b x1 x2. We'll cancel this part, which is b x2 x1. They're the same, they'll cancel. What we will have is alpha times x1 squared plus x2 squared. Okay, but we said this has to be negative. We said this has to be negative, like this has to be negative. And it, since x1 squared and x2 squared both are strictly positive numbers, square of a real number is always positive. It means that alpha has to be negative. So what we found is that alpha, which is a, let's go back a step. Alpha is a real part of the eigenvalue here. Okay, beta is the imaginary part, alpha is the real part. We found that real parts of the eigenvalues of the system has to be strictly negative for the system to be asymptotically stable. We've proven it only for 2D case, for two-dimensional case, but we could prove it for n-dimensional too. So they have to be asymptotically stable. If real parts of eigenvalues are 0, the system is marginally stable. We could, go through the same argument. Say if alpha is equal to 0, it means that this dot product is equal to 0. It means that in our picture the vector x is not going to shrink; it's only going to rotate. Okay. All right. If alpha is positive, it means it's going to grow. X is going to grow instead of shrinking. Do you have questions about this part? Let me be clear. Like this, computing this is not going to be part of the exam, and as an engineer, you don't have to repeat this. Like this is not part of your profession as an engineer. So yeah, this is not something that is necessary. The reason I give it to you is because I think it is useful to understand how this argument can be made. There is a general way to prove this statement, okay. But general way to prove it requires something that is called Jordan forms. That is a specific type of representation of a matrix, which it requires a little bit of technical stuff. That is like, you think like what I showed here is technical? It's not compared to the original proof. The original proof is slightly more complicated. Okay, it requires a little bit more properties of matrices and so on. In my experience, almost always people skip it. Like people don't go back to it professionally. Okay, and what I think is useful is to know that you can, for majority of cases, you can deal with proofs like this, which is much simpler. You know, the more you prove those kind of things, the more understanding you have. So like this is a type of proof that is, I think, easy to work with. So I recommend. But up to you. Okay. All right. Now let me just show a little bit of illustration. So for this system, the vector field would look like this. You can see that it sort of rotates. If you know how to plot a solution based on the vector field, it looks kind of like this. You take an initial point, you look where your arrow drives you to, you take another, take your cue from the arrow, change direction and so on. You keep going. Eventually the arrows will lead you all the way to where the solution converges. I apologize, very hard to draw with the mouse. So this here is the solution. This here is the solution. It approaches origin. All those vectors represent the direction in which the system changes. So basically, those vectors represent x1, x2 dot. Okay. The solution has this kind of rotating quality because it has imaginary part. Eigenvalues have imaginary part. That is a classical way dynamical systems behave when they have imaginary eigenvalues. They rotate. If you're wondering about why rotations are related to imaginary eigenvalues, I recommend you two things. One is to watch some videos about imaginary numbers and rotations. For example, 3 blue, 1 brown, very good videos. That's just a good illustration. And second, try to compute eigenvalues of a rotation matrix. As a robotics student, you have to do with the rotation matrix a whole lot. Compute eigenvalues. You would find that it would have two imaginary eigenvalues and one eigenvalue which is exactly equal to 1. Yeah. So like this would start you on thinking about how rotations and eigenvalues are related. But for now, just remember that eigenvalues, imaginary eigenvalues mean rotation. Right? Okay. Now, this is maybe not like necessarily the most complicated part of the lecture. It is the most general case now that we are going to consider in the lecture. So it should be most complicated. I don't think it will be most complicated. The most complicated we already saw. But yeah, the last one, I think. Let us consider again our system, a x dot equal to ax. So now not two-dimensional, n-dimensional case. Okay, n-dimensional case. I call it a general case, but it's not completely general. It's almost general. Let us assume that matrix A has an eigendecomposition, but the only difference is eigendecomposition is given by complex numbers. So eigenvalues are complex and eigenvectors are complex. Okay, eigenvalues are complex, eigenvectors are complex. Okay, so that's the difference. So previously we dealt with only real ones. Now we have complex ones. Okay. That is basically where the assumption is. There are matrices which wouldn't have eigendecomposition in this nice form. So that is where the assumption comes from. not every matrix would have invertible eigenbases, basically. You can say it that way. Okay, but let's say it does. It does. Then this is very general, so it doesn't assume anything about eigenvalues being real, for example. Okay, we can do exact same thing. We can substitute this equation, this part here, multiply on both sides by U pseudo inverse. So we have it one here, right? One here, one here. And define this new transformation, z is equal to U inverse x. What we'll get is z dot equals to cz, right? Same as before. The steps are literally exactly the same. Right, this is a C, and we have that. The only difference now is that previously we dealt with real numbers. Now Z and C are complex numbers. So that is a big difference. That's a big difference. Those two are complex numbers now. What can we do about it? What can we do about it? Well, let us still do same as we did before, and consider individual equations. Like, as you remember, this is a diagonal system of diagonal equations, so it will be, you know, as they are completely independent. So z1 dot equals to c1 z1. Okay. So here is the like equation number G. Let's consider it. Let's consider it. So independence at least is preserved. That's like, even though they're complex, we still have the independence of those equations. Now, we define C as being equal to alpha plus I beta, just to express how to name specific variables for a real part of the eigenvalue and a complex part of the eigenvalue. This is not an assumption, this is just a naming of the variables. And for Z, we will define real part as U, imaginary part as V. Okay. Now I dismiss subscripts, so those sub j, just so we don't overload us with subscript. I think it is clear. Okay. They're all sub j. Okay. Now we can do this multiplication of two eigenvalues. And we remember that you know, z dot will be equal to u dot plus I v dot. Okay. So u dot plus I v dot, which is z dot, is equal to c times z, which is alpha plus I beta times u plus IV. Okay. Now we can open those brackets, and what we have is A times U plus IBU plus IAV plus minus beta V. Minus beta V. Okay. All right. Now, when we look at this, what we can observe is that we can write two separate equations here. Let me be very clear what I mean. This may be the only complicated part, so let's pay attention to it. We have equations for the real parts, which are here. And we can write it as u dot is equal to alpha times u minus beta times v. Okay. And we have equations for the imaginary parts. So v dot equals to beta u plus alpha v. So beta u plus alpha v. And now comes a punchline. We already know everything about this equation. That's previous example. And we know that for this equation, the stability will be achieved if real part of the eigenvalue is negative, asymptotic stability. Marginal stability if it is non-positive. So we know that for this equation to be asymptotically stable, real parts of the eigenvalues have to be negative. And, marginal if it is non-zero, not non-positive. So the same is true for the whole system, right? Because they're independent equations. And hence, it is the same for the original system, since U is invertible. So we just proven that stability criterion for systems depends on real parts of the eigenvalues. Right? Now, here's the grand statement, which I already made verbally. Now we can see it written. So for equation 21, it is stable if and only if real parts of the eigenvalues of the matrix A are non-positive. And for equation 21, it is asymptotically stable if and only if real parts of the eigenvalues are negative. Okay, that's it. If at least one of the eigenvalues is real parts is positive, then it is unstable. Okay, follows from those two definitions. Okay. Once more, the proofs for specific cases. General proof depends on Jordan forms, and it is well represented in the literature, in the internet classes, and so on. So if you're interested, you would find it. There is no problem. I thought about if I want to give you a general one or this one. I prefer this one. I think that's more illustrative. Some of it, even like this component here, which looks very weird, like this looks very strange, but it has a very nice relation with what we call Lyapunov functions, which we'll see later. So this I think is more constructive, but I don't know. Maybe you later will tell me if you think it's constructive or not. Okay. All right. Now, I think we're out almost. There's a question. Victorina asked me if we're going to finish all the slides today. We have next class at 1 p.m. Am I? Wait. For some reason, I misjudged the schedule. Sorry. We are already late. We are 15 minutes late. My apologies. Sorry. My apologies. Thank you so much, Ekaterina, for reminding me. My bad. I apologize. Okay, there's one slide left. We will discuss it on in the beginning of the next lecture. My bad. All right, I will stop the recording. If you have questions, you can ask me.